Okay, let's talk a little bit about solubility product constants. Th- These are for solids that are sparingly soluble in water. Even if we say insoluble, like we did in the first semester course, that doesn't mean that it's 100% insoluble, so we can calculate a constant for how much really does go in and quantify that. So if we put the quote-unquote insoluble solid or sparingly soluble solid into pure water, and we shake it up to get the maximum amount to dissolve, it would form a solubility equilibrium like I have pictured here. For example, barium sulfate solid is going to be in equilibrium with barium 2 plus and the sulfate ion. So we can write a Ksp equal to the concentration of the barium ion times the concentration of the sulfate ion in solution. And we don't use the barium sulfate that would go on the bottom in a normal equilibrium constant because we don't put pure solids and pure liquids in equilibrium constant expressions. And so we write a Ksp and we call it a solubility product constant. So we're going to write Ksp expressions for these silver salts. Just the expression, we're not doing any calculations. So if we look, I've transferred those over to the paper. And so what is our equilibrium for these? So if that's my solid, there's a 3 there, so we're going to have 3 silver ions aqueous plus a phosphate ion aqueous. So our Ksp expression is going to be concentration of the silver ion, but since this is still an equilibrium constant, that 3 here is going to be cubed in our expression, and then the phosphate ion. So that'd be our Ksp expression there. For silver chloride, again, that's going to be a solid. We're trying to dissolve it in water. It's just going to be a silver ion aqueous plus a chloride ion aqueous. So Ksp will be concentration of the silver ion, concentration of the chloride ion, and that would be a proper expression. If we do it for silver sulfide, last but not least, there's a 2 there, so it's going to be 2 silver ions aqueous plus 1 sulfide ion aqueous. And so Ksp equals concentration of silver ion squared times concentration of sulfide ion. Now, this is for insoluble, quote unquote, or sparingly soluble salts, where the concentrations of these ions are going to tend to be pretty low. But there'll be a range. There'll be some that are more soluble than others, as it turns out. So, in general, the solubility product is the molar concentration of ions raised to their stoichiometric powers. The solubility is the amount in grams of a substance that can dissolve to form a saturated solution. The molar solubility refers to the moles per liter in a saturated solution. So to get a proper Ksp, we're going to need those in moles per liter because we're plugging in moles per liter into those Ksp expressions. So if you get a grams per liter or something like that, you'll have to convert it. And then molar solubility of the salt will need to be converted to molar concentrations of the ions at equilibrium. And then the Ksp is then the product of the equilibrium of those ions raised to their respective powers. And so this is just a little flow chart that shows that. If I got a solubility in grams per liter, I can divide by the molar mass and get moles per liter and get molarity. but I'll have to look at my stoichiometry to get the molar concentrations of the ions, but then I can use my Ksp expression to get the Ksp from the molar solubility. Or I could start with the Ksp and get the molar concentration of the ions and then the molar solubility of the compound. I could also do it backwards. We'll work one of each. So let's look at this particular problem. We got a molar solubility of silver chromate, 6.7 times 10 to the negative fifth. What's the Ksp of the silver chromate? And you can see the equilibrium expression there. Silver chromate dissolving to form 2 silver ions and 1 chromate ion. So we've got that written there. So let's write our Ksp expression. So our Ksp is going to be concentration of the silver ion squared concentration of chromate ion. We don't know the Ksp, but we do know the molar solubility. So if we look at this reaction, let's say I just give it a variable and say X moles per liter of that dissolves, then I would know for however much of that dissolves, I'm going to get 2x moles per liter of silver ion because of the 2 coefficient, and I would get x moles per liter of that. So if this is my molar solubility, that's equal to my x I wrote up there just for space sake. Then my Ksp then, if I plug in that x, is going to be x, right, it's 2x quantity squared, and then that's just x times x. So simplifying, that's going to be 4, the x squared times x is x cubed, so 4x cubed is going to be our Ksp. So it's going to be 4 times 6.7 times 10 to the negative fifth cubed. So then we have to run that through our calculator. So 6.5 or 6.7 times 10 to the negative fifth quantity cubed. Multiply that result by 4. We'll get 1.2 times 10 to the negative 12th. So the bigger and more negative that exponent is, the less soluble the salt is. And so if you're starting to get in the single digits in terms of the negative exponent, you're getting something that's a little bit more soluble. This is pretty insoluble. There's certainly less soluble salts, but this is pretty insoluble. So let's look at one more example. We got, in this case, lead chloride. So we got lead chloride dissolving to form lead 2+, and the chloride ion, and the Ksp is 1.7 times 10 to the negative fifth, so more soluble than our previous salt. But in this case, I have the Ksp and I want the molar solubility. It's a little bit different of a problem. So we can see then, if we want to write our Ksp expression, we're going to have our lead 2 ion and then our chloride ion squared because of the 2 coefficient. And that's going to equal 1.7 times 10 to the negative fifth. Now if I do the same deal I did on the previous problem with the x's, so if x moles per liter of this dissolves, then I would get x moles per liter of the lead 2 ion, and then we get 2x moles per liter of the chloride ion. Plugging that in, we get 2x squared for the chloride, and we get x for the lead, and so we still end up with 4x cubed for our answer, but now it's set equal to 1.7 times 10 to the negative fifth. And so instead of plugging in for the molar solubility we were given in the previous problem. Now it's set equal to the Ksp in this problem, and we need to solve for x. So we've got 1.7 times 10 to the negative fifth divided by 4. So x cubed is going to be 4.25 times 10 to the negative sixth. And then I'm going to have to cube root both sides. And so depending on your calculator, you may want to raise that to the 1/3 power, depending on how your calculator is set up. It's the same thing. And so x then is 1.6 times 10 to the negative second. And that is a molar concentration, because this is our molar solubility of that particular salt. Lead chloride can be somewhat sparingly soluble. It's starting to approach that sparingly soluble range instead of just insoluble. Usually, and these are just basic rules of thumb, we say something's insoluble, which we know is not truly 100% insoluble, but we say that solubility is negligible if you're less than 0.01 molar. If you're between 0.01 to 0.05, and again, these are rules of thumb, not hard and fast principles. We would call this sparingly soluble. And then if you're greater than 0.05, a lot of people consider that soluble. But just because this was just above that, we're calling it sparingly soluble, but is it really that much more than something that's slightly less than that? So what you got to realize, it's more of a sliding scale than hard and fast black and white either or sort of principles. And go back to this first semester material and review our discussion of solubility in water, because that'll give you some good principles of what should be soluble and what shouldn't be. Things that are insoluble or sparingly soluble are going to be the ones we work these types of problems for.